This is the Virtual Engineering Solution. The virtual engineering system is a process technology that helps semiconductor companies use advanced 3D and 4D technology to reduce costs and improve turnaround time for the total manufacturing and packaging of semiconductor devices. This video will cover several topics. First, we'll discuss some of the issues semiconductor companies face today. Next, we'll discuss some critical factors to consider as we develop solutions for the issues. Then we'll introduce the virtual engineering system, covering some key strategies along the way. So, prepare to be amazed as we show you how you can benefit from this new development. Semiconductor companies today face a number of increasingly complex technology and process problems. Two of the bigger problems are long time to market and turnaround time cycles, and high costs associated with materials, labor, and assets. These problems eventually lead to low profit margins across the industry. The reasons for these problems are varied, but they include packaging that is becoming increasingly complex, especially with virtual technologies such as stacked dies, systems in package, modules, embedded devices, 3D packaging such as package on package, etc. Miniaturization of packages, die shrinks, and challenging design rules in the manufacturing technology. Long development times in both R&D and production, especially related to the design stage. Too many design manufacturing spins before achieving high-yield products. Challenging verification of package properties for electrical performance, thermal and stress characteristics, etc. Higher speed devices. Industry pressures to bring products to market quickly, and fierce competition. In developing the virtual engineering system to solve some of these problems, we focus on three primary concerns. First, we consider business concerns, time to market and turnaround time, productivity and profitability. To meet these concerns, we want to make every process faster, we want to make every process more efficient, and we want to manage costs. Next, we consider engineering concerns, product quality, product speed, and product performance. To meet these concerns, we want to reduce errors, we want to optimize performance, and we want as much as possible to simulate through software every part of the process before proceeding to manufacturing. Finally, we consider environmental concerns, waste, green materials, etc. To meet these concerns, we want to replace as much physical prototyping with virtual prototyping. In short, we want to move the product lifecycle curve to the left as much as possible, meaning that we will ride the wave as quickly as possible and for as long a time as possible, in order to capture and maximize the revenues available in the market. In the next few chapters, we will introduce the three key strategies to implement the virtual engineering system: concurrent design engineering, collaboration, and visualization. The first key strategy of the virtual engineering system is concurrent design and concurrent engineering. These are concepts that have to do with working on separate processes concurrently. It is the idea that we can change from a serialized total process, in which a process must be completed before the next process starts, can be changed to a parallel process, in which a certain amount of parallelism exists, and individual processes can become only partly dependent on the completion of prior processes, or ideally, can become fully independent and can be started at any time. Process parallelism has the potential to be achieved in various areas in the semiconductor industry. For example, between IC chip design, IC package design, and PCB design. Between various types of design and simulation. Between design and manufacturing. As a result of creating concurrent processes, companies can immediately start realizing time and money savings, and this provides the first step towards building an efficient virtual engineering strategy. A practical application of concurrent design engineering is the cockpit. The cockpit is an application for sharing of information and data. The cockpit includes facilities to manage database information and files, view, work with, and share information and data with other users of the system, review and mark up projects, view standard PC information such as schedules, design inputs, and etc., communicate with other users, and keep track of key performance indicators. Let's take a look at the cockpit in action. In this example, we have two users on separate PCs. These may be users across the room or on different continents. The user on the left is designing a wire bond fan-out. The user on the right is an assembly engineer that is working on wire bond assembly profiles. The users want to work together to determine a fan-out that is satisfactory for both the design and for assembly of the package. On one of the user's PCs, or on a separate PC, for example a manager, two connections are built. As the wire bond engineer moves a substrate bond finger in the 3D environment, the cockpit program dynamically connects to the engineering CAD applications and the database, and in real time updates the wire bond fan-out in the 2D environment. At the same time, the designer wants to move the substrate bond fingers in a different way. This change in the 2D environment is reflected in turn in the 3D environment, also in real time. Based on the benefits of this type of concurrent activity, the designer and the assembly engineer can decide on a good wire bond fan-out that will work for both the substrate and the assembly manufacturing. The second key strategy of the virtual engineering system is collaboration. This is a concept that has to do with helping users work with each other. In other words, how can users share the data? There are three major types of collaboration. Human-to-human collaboration. This has to do with enabling functions and technologies that can help people collaborate while they are located in different facilities, countries, companies, and across various barriers such as language and culture. Human-to-machine collaboration. This has to do with how people can collaborate with machines, whether the machines are software or hardware. In this case, it is important to consider how people will understand the software and the hardware, including user interfaces and data formats, and how people will understand the information and know-how that is stored in the systems. Machine-to-machine collaboration. This has to do with how machines can work with other machines. Part of this includes the interfaces between different software systems and interfaces between different hardware devices. Data formats are important here, not just in terms of compatibility, but wherever possible in terms of direct communication. The other part of this collaboration is interfaces between software systems and hardware devices. Again, data formats are important, but so is information and knowledge storage. For example, to control a hardware device, the software system should know how to communicate with the hardware, but ideally it should also be able to optimize it and control it directly. The virtual engineering system makes frequent use of direct interfaces between not just the different players in the company, but also between different processes. This is the key to enable the concurrent design engineering aspects of the system. Every process must be able to share and understand information and data with every other process. Let's take a look at a case study. A designer using a 3D package design system wants to transfer the design information, including 3D models, to a 3D electromagnetic simulation system. This includes material stack-up information, such as heights and thicknesses, interconnect information, such as netlist data, pin numbers, parts, etc., and endpoint bond wires, meaning bond wires that are detailed, accurate, and realistic. For example, not limited to simple models. The idea is to transfer the data such that the simulation system can read the data and immediately be ready to simulate. There is no extra setup to rebuild geometry, define bond wires, solder balls, ports, etc. There is also a desire to avoid using formats that, although standardized, can only carry dumb information, and instead use intelligent formats that fully support 3D and all electrical information. The virtual engineering system supports such transfer of information by specifying native formats using accurate 3D data models for all output to mechanical, stress, and thermal simulation systems. The direct links also allow transfer of design information to most popular electrical simulation programs for parasitic extraction, linear simulation, and electromagnetic analysis. Finally, the links are capable to output intelligent information at any stage of the design or manufacturing process. In addition, there are applications to support manufacturing data feedback through a patented PWO-XBWO process. This allows a user to take an optical or X-ray photograph of a package after wire bond assembly or after molding and bring all data back to the 3D system. Everything is rebuilt accurately, making it possible to do failure analysis, optimization of the package assembly, and non-destructive measurements. A further extension is to allow the design system to communicate with and control the manufacturing equipment directly. For example, a wire bond fan-out can be created and optimized by the designer. Then the results can be read to and from the manufacturing equipment or to a database. In this way, a knowledge store can be built that contains important information and know-how about the entire process, and future designs can be created using known good data on the first try. The third key strategy of the virtual engineering system is visualization. This is a concept that has to do with how complex assemblies and package constructions can be visualized and understood by using 3D and 4D technologies. We could say that 3D and 4D is a key enabler of other strategies. We should note that other industries, such as automotive and aerospace, long ago adopted 3D as a key infrastructure technology and have realized a number of important benefits in improving the total life cycle of products. This has given rise to many products that brand themselves as PLM systems. However, in semiconductors, use of 3D has been at best limited. By the way, what is 4D? In Euclidean geometry, we can describe three spatial dimensions, which correspond to length, width, and height in a typical 3D modeling space. If we continue to the next dimension, the Euclidean fourth dimension is a tesseract. But that is not what we mean here. We are talking about a different fourth dimension. We are talking about the Einsteinian concept of the fourth dimension, namely time. We are concerned with modeling what happens to semiconductor devices and packages over time. So what is needed to bring 3D, 4D to the semiconductor manufacturing process? Quite simply, we must represent everything about semiconductor packaging manufacturing through software. We have to model the package using 3D solids, verify the package in 3D, simulate the process in 3D and 4D, and animate the process in 3D and 4D. That is what we mean to visualize the process. First, some basic concepts. When we talk about solid modeling, we are referring to how 3D primitive shapes are created and manipulated. A simple example is to look at constructive solid geometry. 3D solids can be formed easily by starting with simple shapes and either extruding them in another dimension or by sweeping the shape along a path. Complex 3D objects can also be modeled easily and parametrically by performing Boolean operations, such as combining objects, subtracting one from another, and etc. Photorealistic models can also be created by applying various types of rendering techniques to basic wireframe models, such as shading, texturing, and lighting. Specifically, for semiconductors, a method to model and manipulate complex parametric objects such as wire bond profiles and capillary tips is also necessary. Next, 3D verification refers to the application of design rules to the package construction. This refers to static spatial clearance and interference checks of objects that do not move. The program must check and then report any errors once a 3D model is created. 3D 4D simulation refers to the simulation of a process and doing the verification throughout the timeline of the process. This refers to dynamic spatial clearance and interference checks, such as checking the bonding capillary does not violate clearance rules to or crash into existing objects such as bond wires or chips. To make this kind of process simulation possible, it is important to consider other factors, such as manufacturing equipment tolerance. For example, this refers to simulation of the die's bonder placement accuracy to test the worst-case conditions. Inputs directly from manufacturing equipment, such as wire profile geometries, capillary geometries, and toolpath trajectories. The fourth dimension is a summary of the timing of manufacturing sequences, which must be carefully analyzed to make the 3D, 4D simulation possible. Finally, 3D, 4D animation refers to bringing the entire process to life. For example, the system makes it possible to capture data from video devices. The user can then rebuild the 3D model using the video as a model, and the resulting animation can reveal at any desired speed the details of the process. Another type of animation is to recreate processes that cannot be easily observed, such as the molding process. In this case, using the PWO, XBWO components of the system, the before molding and after molding conditions can be extracted and the animation can simulate the molding conditions. We can also refer to this type of animation as an example of volumetric morphing. Here we introduce the virtual engineering system. The heart of the system is its virtual engine, which supports the necessary 4D requirements we have described, including the visualization functions, the concurrent data links to communicate with various other systems, and the collaboration operations support to integrate with various system tools, such as the cockpit and the system database. This virtual engine provides the most robust environment to help design and simulate any kind of package constructions imaginable, without any kind of limits. The design solutions wrap around the virtual engine to provide all the necessary design tools, including CAD links to various industry standard design systems, simulation systems, and documentation systems. Design functions suitable for both production or R&D work of all packages, PCBs, schematics, and etc. Part information management, including various types of parametric libraries and visual libraries, and remote collaboration design and development functions to allow collaboration systems like the cockpit to access and manipulate the CAD systems. The database functions also wrap around the virtual engine to provide the storage capability for the system, including bill of materials management, documentation management, project management, engineering management, and intellectual property management. Various types of system solutions connect to the core part of the system. System solutions are more than plug-in components to the system. They are solutions that enable some important form of communication with the system to provide a compelling business benefit for its users. The solutions include the Design Review Solution. This solution is a project planning solution that gives users the ability to make conceptual what-if scenarios concerning the package construction. For example, it is possible to quickly test whether a particular chip fits in the package in combination with another chip, or which chips fit best on the top or on the bottom in the case of a die stack. This solution may also be connected with other solutions to provide additional details, such as the amount of materials required, viability, and the assembly wire bonding, and etc. The TSFA Online Solution. This solution stands for Technical Salesforce Automation. It is custom made for users that may not be familiar with engineering or CAD tools, but still need an easy-to-use and easy-to-learn tool to make quick, feasible studies. For example, a salesperson can go into the field, take basic chip inputs and requirements from a customer, and within 30 minutes generate a report of a package construction that includes a wire bond fan-out, the 3D model construction, and a report on any assembly rule violations, including in 3D or 4D. In combination with other solutions, it may even be possible to provide an instant quotation about the packaging, reducing a typical process from days or weeks to a matter of hours. The FAQ Management Solution and the Knowledgement Management Solution. These solutions provide the capability to store important information and knowledge in a database for easy retrieval and reuse. This makes the jobs of maintenance and quality control much simpler, as relevant knowledge is easily accessible in digitized format. The ECO Efficient Solution. This is a solution to provide details about the environmental friendliness of a package construction. The solution uses standard information to determine typical materials and the impact they have on our natural resources. The CIM Solution. This stands for Computer Integrated Manufacturing. Given the rich set of features in the system to communicate with and control manufacturing equipment, this solution provides important methods to communicate with equipment. It is possible to establish and standardize repeatable processes with manufacturing excellence using techniques for the next generation factory automation. For example, wire bonded data can be read into the system and build an intelligent database of loop profiles. Then, the 3D/4D simulation can run completely on actual manufacturing data, and the system can generate files that are optimized for a specific design in the language of the wire bonder. The data files can be plugged back into the wire bonder, and the wire bonder is ready to start with no extra teaching necessary. The failure analysis solution. This solution provides the necessary manufacturing feedback functions to analyze the package construction during the manufacturing stage. Using optical or X-ray photography, the system can easily, quickly, and accurately rebuild complex models for use in the 3D/4D simulation engines. This is a form of non-destructive analysis that makes previously invisible information completely transparent. The virtual solution. This solution is for R&D prototype samples and includes all of the modeling and simulation programs necessary to take full advantage of the system's 3D/4D architecture. The virtual engineering system has tangible benefits and applications in various parts of the design and manufacturing process. For example, during the pre-design stage, the package feasibility can be run to give the user an important visualization of the package construction. Beyond the technical benefits, such as verification checks, this can give important ideas to non-designers and non-engineers. For example, managers, salespeople, and customers, to understand the products and their applications and to communicate important points. During the fan-out design stage, a chip designer can work with the package designer to determine the best I/O pad placement on the chip. This can later reduce the amount of time that is spent on the package design, a critical place to cut time from the overall process. During the 3D/4D base wire optimization process, the designer and the assembly engineer can work together to create a solution that is simultaneously good for the package design as well as for the wire bond assembly. The resulting models can give everyone a good visualization of how the total assembly will come together. More importantly, because actual manufacturing data is used in the optimization process, the process can deliver known good results before any manufacturing is ever done, resulting in first-time success every time. During the product verification simulation stage, the designer and the simulation engineer can exchange data quickly and easily, using the native formats of the simulation system. This leads to greatly reduced cycles for design simulation and can ensure that every package is properly simulated, resulting in higher quality and more robust products. During the failure analysis stage, actual manufacturing information can be brought back to the design stage, enabling everyone to learn from problems in manufacturing. In addition, the knowledge can be saved digitally in the database so others can benefit from the stored up knowledge. This also frees up more time for future packages to incorporate optimized data and information, leading to continual improvement in the product quality. The virtual engineering system provides important solutions to help maximize the effectiveness and efficiency of every process. The rich visualization provided by the system allows its users to understand the technology and products in ways not previously seen in the semiconductor industry. This adds substantial benefit, especially for cutting-edge organizations, to be more creative in exploring new kinds of technologies and solutions, while keeping sight of cost-effective processes and methods. As we discuss virtual engineering, it is important to always analyze the typical design lifecycle. Some people may wonder, it takes more time to do 3D, 4D. If we are already making products using 2D design, why go to 3D, 4D? Well, that's right. It does take more time to also do 3D, 4D analysis. So why do it? Because if you relate everything to the product lifecycle, you might find that although extra time is required for 3D, 4D, so many benefits can be realized in other areas, including in the design itself, that the benefits far outweigh the extra time spent. We can see two examples from existing customers of the system. One customer was doing prototype manufacturing and wanted to cut the time spent on R&D. By using the system, they were able to change to a software-based R&D process. The design still took the same amount of time. However, they were able to do all of their typical fabrication and assembly processes in software. This became their virtual manufacturing laboratory, and they reported 60% time and cost savings as a result of the process change. Another customer wanted to cut the total design time, but they also wanted to change the focus of the design. They found that complex wire bonding required more time that they could afford because they spent too much time routing the complex designs. Using our system, they were able to develop routing tools and strategies to greatly reduce the design time so much that they could now afford to spend more time on the wire bonding optimization, while still reducing the total design time. With the virtual engineering system, companies are realizing a number of important benefits, including higher quality products, faster time to market and reduced turnaround time, and overall lower costs. Through the use of virtual engineering, 3D and 4D technologies enable next-generation semiconductor factory automation. To this end, our system provides the ability to accurately model and simulate all aspects of manufacturing and assembly, all characteristics of design information, and all characteristics of manufacturing information, and accurately predict material usage, detailed cost structure of the product, schedules, and potential problems. In conclusion, a virtual engineering system strategy can help companies to reduce turnaround time and time to market, reduce costs, and improve profitability, quality, and productivity, while considering business, engineering, and environmental concerns. By implementing new 3D and 4D technology, which benefits the company, the industry, and the planet. Thank you for your attention. If you would like more information on our company or on our system, please feel free to contact us anytime.